focus on the solid lines here. The two solid lines represent two performance we using different membrane widths. As you can see here, the larger the membrane width, the better performance it is. But of course, the membrane width is limited by the overall size of the sensor. And the dot, all these dots here are the experimental result using the microscope, not the X-ray, or using the microscope first to have a better accuracy first. We can see that the overall performance in practice is quite matched with predict theories, especially within the range of the human blood pressure. Because we are talking about human blood pressure only. And in the future, if in the real practice, for the relative large pressure, of course, we still need some little offset for these narrow values. And many other performances are also tested here. First thing is the sensitivity, which means the increasement of the length and the different pressures. So in the previous speech, we can see that the relationship between the pressure and the length are not linear. So the higher the pressure, the lower the sensitivity. You can see here from this one. But even seeing that, even for the lowest sensitivity, we are still, based on current image technology of the X-ray, we are still able to see the difference of the blood pressure when the restenosis happens. But of course, if by using the lowest sensitivity, of course, we cannot get a very accurate reading of the pressure, but definitely we are able to capture the pressure drop of the restenosis. Another thing is maximum pressure the system can withstand, because we don't want our blood pressure to destroy the overall sensor. So by using a simulation test form, the maximum one massive stress was estimated under different blood pressures. By all the output values here are far away from the limit. We can see that it's one order lower than the limit. So basically, we can see that the membrane is strong enough to withstand the blood pressure. The next one is the hysteresis performance, because we want to get the same result for the same pressure in different measurements, because it's a periodic measurement. We want to test it again and again and again. And of course, in this test, we can see that all the output performance are mirrored to each other, which shows that the hysteresis performance are relatively good. Okay, so when we come to the X-ray test, we put the sensor into standard chest pattern, which means it's a dummy human body that's used for the medical radiation test purpose. And using two special SP sensors. One is completely filled manually. One is just original with a reservoir field. That's to simulate the pressure difference, to see whether we are able to see the length difference and the X-ray image. We can see the image C here. This is the processed image of the X-ray. We can see this is the field gauge. You can see the difference here. This is a half field. This is a no field gauge, so we can see the length is definitely shorter. We can see so definitely it's obvious to see. And the next one is a liquid. Another one test is a liquid column length variation test. That means put the sensor into a pressure chamber so that the pressure can be controlled. And by using, we can see the X-ray, the length of the gauge, the length of the liquid in the gauge, and the different pressure. Also, we see that the resolution is not relatively high, but as we said before, it's still good enough for detecting the restenosis, because the restenosis definition means 30% of the blood pressure drop. The normal human pressure is about 120 about that. So 30% will be over about 35 mm Hg. So definitely we are even using 1 to 2 pixels is enough to detect the pressure drop bit. So definitely it's useful. But of course, it's not that accurate to measure the blood pressure. So here comes the conclusion. It has very lot of the probe part. It's very small in size. The width is only 1 millimeter, and it don't need any battery. It's a passive component. It's passive sensor. It don't need any electronic component, and also it's the monitoring process don't need to cut any part of our human body. It's non-invasive. It's not expensive. You just do one X-ray test. It's just maybe $100 or something. And it's have a relatively low radiation exposure, because as compared to the CT or other methods, just the X-ray test is very low radiation. So that makes it very suitable for periodic monitoring of the restenosis. For the disadvantages, the major one is low resolution in standard X-ray image, as we can see in the previous page. The resolution is definitely not that high. Another one is in the paper, the long-term reliability is not tested, because if we really want to put it into the real use, definitely we need to get the long-term reliability performance. We want it to be useful for maybe for 10 years or longer. Okay, for the future improvements, future improvement is focused on the low resolution. First thing is we may use a thinner or wider membrane so that the volumetric displacement could be larger, so that the gauge length could be longer, so that making it more visible. Another one is using a more modified X-ray machine, using a special design X-ray machine so that it can be focused on that spot, so that the resolution could be higher. The last one is using the more higher contrast agent. Currently, we are using the very commercial one agent. Maybe we use some like the golden nanoparticle suspension or something like that to make it more obvious to see in that image. Yeah. Okay, I think that's all for my part, and also that's all for our group. Thank you for your attention. Thank you.
Okay, your team also on the other swing of the boundary, having totally different papers. All right, okay, so let me start from the first one for Mohammed, right? In this design, what is the sensing mechanism? Can you highlight again? Basically, it is VCO as a sensor, right? So can you describe the sensing mechanism? The VCO, well, what's the shape of the VCO first?
The shape?
Yeah, it's just a device on the substrate, or it's a release structures?
This one, let me just go back. I think this is the sensor. I'm not the VCO, but I think for this case, it didn't really show it in the paper. They were just focusing more on the sensor itself. Yeah, the sensing mechanism, the transistor, I think they are using some kind of electric, measuring the dielectric constant of the fluid that flows through the channel. So the transducer will be the one converting it to the one to be detected by the detector itself.
You mean the dielectric constant of the liquid holding in the free channel?
Yes, right.
And the free channel itself become a kind of a capacitor or even inductor?
They didn't really say specifically, but they were detecting that change in the dielectric constant in the paper. Yeah. Because, like mentioned here, the different liquid will actually change the voltage of the detector itself. And through the simulation, you can see that they are actually at 115, because that's the one that the VCO was tuned. So the VCO was tuned at 115 GHz, whereby it was giving 0 voltage. And then when we are using for different fluids, they are actually shifting the detector output itself. So that's how we detect the change in the liquid itself.
Okay, probably I come back to here later. So we move to the second paper. Yeah, digitized microfluidics is one of the research area. Right, even one or two colleagues in NUS are also working on these devices before. So what if we want to suggest a disadvantage of this approach, then what will you say?
Disadvantage.
Yeah.
Let me see. We need to prepare the solvent because the biomarkers are all contained.
It's common practice, not in your domain knowledge,
okay.
but for biologists, it's like 3 meals per day, right? It's a daily practice, no question,
Okay.
no worry. Yeah.
For this one,
From engineering standpoint, right, what's the disadvantage of this technology? It is good in many aspects, right? But what's the disadvantage?
the robustness might be.
In which way you
Because
the robustness?
there is no carbon, no nothing. It's easily
I agree
contaminated.
with you.
Yeah.
There's one more.
One more. How reliable it
We
is.
want to move to the page 16.
Page 16.
Yeah.
This way? This way.
16. This one, yes.
Maybe it's not fully removed from the solid.
Depending on different type of
sample.
liquid.
Two different droplets can mix better, much better.
That's the purpose, right? You want to
Yeah.
mix it.
I cannot think of other.
No, the answer is here, right?
Yeah.
It's more related to the control, right?
The control part.
Mm.
Okay. The electrode
Mm-hmm.
is conductive. Might be.
Or Xingyi have a feeling.
Size of the electrode is limited.
You are doing FYP events, right? You probably another expert, right? Any
Can
advice?
control the size of the droplets by the size of the electrodes in this case.
Not the advantage, right? Not the disadvantage, right? We are talking about disadvantage.
Is it the throughput?
There are
is
many
very-
advantages for this technology, I agree, yeah.
Is it because the throughput is not very high?
Not really.
These sort of things, no, if you compare to conventional approach, right, throughput still quite good, right?
Oh.
Compared to other microfluid chips, it's hard to say, right? It's case by case, right? But there's a disadvantage in general in comparison to other microfluid chips, right? We move to the next paper first. We can come back later.
Okay, thank you. I'm thinking.
Think about it, right? The answer from that page. Right? So actually, you report two approach, right? So the first design showing the method one, probably page 22, right? Actually, this page. Yeah, next time you guys all need to remember to add in the page number, right? Then actually this one has been used in the page 25, right? So by using this way to deform it, right? Am I correct if I,
This one is for calibration.
for calibration?
Yes. The
But for the
actual
real measurement, the
the
cell
real-
will be placed
will
at the,
be like the real measurement. Then because it's electro, so it's rubber around something like AMM. And then here actually got the pillars, so it press down to the cells, and the pillar will contact with the cells.
so can you move back to the page 22? So when you say the pillar is a pillar made of SU8, that one will face to the cell, press to the cell.
Yes.
I see.
And because it is gold coated, so
Then we are measuring the resistance change.
Yeah, both resistance. Yeah, both from the conductivity of the cell itself, and the deformation of the pillar on the substrate. So because this is mechanical part, so when we
Can
press
you
contact
move to the previous page? Yeah, here.
Yeah.
So SUA is not conductive, right?
So they coated with
So
gold.
where is the pattern? The figure A, right? Where is this strain gauge pattern locate?
Oh, this one is actually the string, and it's here. And then they coated with the
Oh.
pillar. The pillar is conductance because it got some gold coated on it. Like the gold is coated on it. So they actually coat the gold on the top surface and got some link between this and the conduction part. So they actually form electrical parts.
I see. So I saw the side paper. Is it from the Caltech?
This one is from the University of Maryland. The
Okay.
next one is from the Caltech.
So to you, you feel the second approach is better?
Yeah, before early detection, the second is better because I think the
Can
first
you
one.
move to the personal comment?
Personal comment.
The last one. Right?
This one or next
No,
personal?
last one.
Okay.
So actually the two approaches are slightly aiming for different
Yeah,
purpose,
for aim
right?
for different purpose.
Yeah, the
Because,
first one is more like
yeah.
to
Detecting the
check
certain
out the-
location.
the mechanical property of the CTC, right?
Yeah.
So in this regard, what's the difference in terms of mechanical property between the healthy cell and the CTC?
The healthy cell is more stiffer and the conductivity I think is more. Yeah. So it's stiffer and elasticity is larger, and this is from the mechanical detection, and from the electrical detection, the resistance of the pinac cell is larger.
Okay, we move to the next paper.
Yes.
Yeah, next paper is more like a practice of the exam, right?
Practice of the exam.
Exam question.
Oh, is it?
So, if we want to enhance the resolution
Oh,
of the OCT, right?
okay.
Resolution meaning if you look at the page 48, right? When you do the cross-section scanning on the right-hand side, right? Then get the better image, right? Okay? Then in that way, what's the potential way you can do in terms of the mirror design so you can make a better resolution here? Do you want to move back to the page 43, 4 page earlier? Can you move back? No, one more. Yeah, here.
Okay. So the question is, how?
If you want to get a better resolution in terms of the taken image, right? What can you do in the design of the mirror so probably you can gain higher resolution?
Oh, okay. So I think to have yeah. Actually, if you want to get a higher resolution, it means we have to increase the frequency, right?
Yes.
Yeah, it increase the frequency.
Okay, then in terms of increase the frequency, can
Okay.
you move to the previous page?
Oh, okay. This one.
We don't need to make the video long. Yeah, here is also fine.
Okay, okay.
Either way, here is also fine.
Okay.
Can you suggest how to do?
Reduce the mass. Reduce the mass of the
Which
mirror.
part can you pinpoint to the?
Yes, yes. This one is the mirror, right? So if we can reduce the mass, we can have a higher resonance frequency.
Reduce the mass of the mirror.
Yes, first thing.
Okay.
And second thing, to make the, of course the, we have to design a torsion spring with a more rigid torsion spring, so that the resonance frequency can be faster. Yeah, that's just two solutions.
But in the meantime, when you increase the rigidity of the spring, right? What's offset what's
Okay.
disadvantage
Yeah.
quality to the mirrors.
Yeah, the consequences are if we increase the rigidity of the torsion spring, we will reduce the deflection angle. We will reduce the deflection angle so that it will, yeah.
Okay. So we move to the next paper.
By the way, I want to ask some questions. Is it okay? So I just think, how about if we use two mirror for the vertical, we separate the mirror for the vertical mirror and the horizontal?
In the OCT application?
Yeah, I think it's not possible. I think.
Depending on the packaging, right? Normally people will not do so because the diameter of the OCT package is very small. My understanding is around 3 millimeter in diameter to 4 millimeter. It's quite small. So two mirror approach is there, but not designed for what you want to do. It's designed to make a 36 degree of scanning of the mirror. If you only have a single mirror, right, no matter how you do, right, roughly you only, the maximum is 180 degree.
Yeah.
Yeah, so there's a design to achieve a 36 degree surround the whole head of the OCT head. Yeah. Okay.
Thank you.
Yeah, Chung-Hao. So, well, very interesting. This is the first time I learned this kind of a device. I didn't notice there's a technology like this. So in the probably next, here, right? So the liquid called ISO view 370. What is the liquid it is?
Basically, it's an organic component. It's very complex.
Okay.
So, like a protein or something. Very
And
complex
what's the
structure.
function of this one?
It's working as X-ray. Basically, working as an X-ray withdrawal fluid, X-ray agent, so that we are able to see it through X-ray image.
Okay.
It's very, I think it's very common in the medical.
So it's a liquid will absorb the X-ray.
Yes.
Okay. So in terms of the design, what's the difference between the proximal sensor and also distal sensor? There are two positions, right? They are
yeah.
same design.
Same design, exactly the same. They are just designed to detect the pressure. You see this is incoming pressure, this is the output pressure. They are just to detect the pressure difference. So as long as the pressure difference is no larger than the 25 to 30%, we can see it's still good. But if larger than 30% of pressure drop, we see if there the restenosis happens, maybe this could be fatal, could be threatened to people's life.
Mhm. So in the second last page, right, there's X-ray image, right?
Yes.
Did the other make it in the real human test, or it's a demo? It's not really in the human.
It's using a chest phantom, it's a dummy human body.
Oh,
That's
dummy,
it. That's
okay.
widely used in the medical radiation. So basically, you can see that it will be if we use a human body, it will also show like this way. You see, it's and also the sensor is also.
So that in the figure D, right? What exactly of the dimension is it?
Oh, which dimension?
The size of the stand and also the sensor. Right?
The stent, I'm not sure, but the sensor, the width is 1 millimeter. The length is 15 millimeter. So basically, we want to inject into the blood vessel, so the width should be smaller. But the length can be a bit longer.
So you
Yeah.
come up with the answer.
Yeah, two options. Okay. One is only 2D, it's only two-dimensional. So compared to other microfluidics, also 3-dimensional. The other thing is it's a disposal, like let's say such complex device can be only used for once. That's my answer.
Yeah, I think the point is to make this one operate as beautiful as the video, right? Actually, you have so many electrode,
Yeah.
and you have so many bonding plate outside, right? Meaning that the control of the electrode is quite complicated.
That's true, yeah.
So you have to do in terms of time sequence, also in terms of the amplitude of the bias applied.
Yeah.
A lot of power meters also not so easy.
Okay, the control path.
Yeah. Anyway, all the papers are not really relevant, so maybe very hard to make a general question to all of you. So probably we sometime stop here. Okay, thank you very much. We move to the next group.